Hello and welcome to the second video for section 5.3. We're still dealing with sine and cosine curves. The only difference now is this will be talking about amplitude, period, and phase shift. This will be the heart of the types of graphing that you're doing throughout the semester. You'll be given a trig function or a trig graph, and you'll have to do some manipulation to it to graph it using these different options of amplitude, period, or phase shift changes. So, first in general, for general functions, y is equal to a times sine of x, or y is equal to a cosine of x. If we take the absolute value of whatever the value of a is, so this could be plus 1, it could be minus 1, plus 2, minus 2. If we take that absolute value, the absolute value is called the amplitude. And is the largest or if you want to think of it as the furthest away from the line that these functions attain. So again, if we try to think back to some of our basic functions, x squared, x to the third, square root of x. If we put a number in front of there, what happened? It just made it bigger or made it smaller. And that's the same idea going on here. So I'm going to erase this. We'll work an example. If you need to pause it for a second, come back, that's fine. Alright, so let's look at this example. If we want to graph y is equal to 3 sine of x. So as before, we want to deal with first, what's our basic function we're talking, our function we're talking about? It's sine of x. So if we recall, we have pi over 2 and pi, 3 pi over 2, 2 pi. If we are dealing with just sine of x, we're starting at the origin, going up to 1, through pi, down to -1, ending at 2 pi. But this 3 in front now tells me that I have to multiply every value that I have on this graph by 3. So I start at 0. 0 times 3 is still 0. So I'm still at the same starting spot. But here I is at 1. So 1 times 3 is 3, which gets me as high or as far away from this graph as 3 units. Here I'm back to 0. 0 times 3 is still 0. But now here at 3 pi over 2, my value was -1, but -1 times 3 is -3. So this comes down as far as 3 units. So that's why we had that absolute value. We're still 3 units away. It's just to the negative side in this case. And again, back up to 0. So this function, y is equal to 3 sine of x, is this red line here, where it's basically stretching this sine curve so that every unit is increased by a multiple of 3. Now I want to point out here to be careful. Notice we did not shift this 3. This was not sine of x plus 3. And I'll see that problem a lot with people is they see this 3 and they think that the whole thing has to move up 3. Make sure you're clear with that distinction. If we just have a number in front multiplying by the function, it's strictly just a multiplier and it's stretching everything out. Okay, so that's amplitude. Now let's talk about period for a little bit. So the sine and cosine curves so y equals a sine of kx. So now what we've done is added another value here inside the function. So between sine and x, we're putting some other number. Could be 2, could be a half. It's going to be some other number. Or y is equal to a cosine k times x. And again, both of these cases, k is some number greater than 0. Could be a fraction, could be a large number, but it's positive. When we have the equation of this form, so these curves have amplitude, same as before, absolute value of a. And period of 2 pi, because that's what our typical period was for sine or cosine. If you remember, period of sine and cosine is 2 pi. But if we put some number in front of here, the period now changes by 2 pi over k. So if I had a 2 in here, if I had cosine of 2x, then it would be 2 pi over 2, or just plain pi. So it's actually shortening down how quick this thing makes a complete cycle. All right, let's look at a couple examples. So let's say we want a graph. The first one is y is equal to sine of 2x. So our amplitude here is what? It's 1. It didn't change anything there in terms of how high or how low sine gets. But it did change our period. We have our k is equal to 2. So that means if I want to write these down, my amplitude is still 1. So I get as high as 1 or as low as -1. My period is 2 pi over k. So 2 pi over 2. The 2's cancel and give me pi. Which means instead of taking 2 pi units to make a complete cycle, it's doing it in half the time. It's doing it in a distance of pi. So this is where I'll introduce to you a way of when we have to start graphing these transformations, how to make it easy on ourselves. So I told you before we had those 5 marks, 0 and then the other 4 dashed lines. So these dashed lines before were what? They were pi over 2, pi, 3 pi over 2, and 2 pi. When we start doing transformations that are a lot more complex that we'll see here at the end of 5.3, these points are going to change on us. And they're going to change based on a period or based on phase shift, which we'll learn next. So if we write down what the original value should be, then the second step is to divide by k. Excuse me. So in this case, I want to divide everything by 2, because my k is 2. So pi over 2 divided by 2 is pi over 4. And pi divided by 2 is just pi over 2. 3 pi over 2 divided by 2 is 3 pi over 4. And 2 pi over 2 is just pi. So I still have the graph that looks the same. So it goes as high as 1, goes as low as -1. But now these points where it's crossing, if all I have is a period change, are these new numbers. I didn't have to do a bunch of calculations with fractions and all this kind of stuff. I was just able to divide by k. So this point here is pi over 4. This one here is pi over 2. This one is 3 pi over 4. And this one is pi. This is where you can check yourself. We said that period up here was what? It was pi, meaning that the sine curve should make one complete cycle in a distance of pi. Well, you can see that with our numbers, they match up here. Pi is the same as what we calculated the period to be, so we can be pretty confident that this graph is a correct representation of our original equation, y is equal to sine of 2x. So that's our example there. All right, let's look at another example. So our second example, let's say we want to graph y is equal to sine of 1/2 x. So again, our amplitude is still 1. The value in front of sine is 1. We don't see it, but it's there. It's the 1. Period has changed again. But now our k is equal to 1/2. So the period is 2 pi over 1/2, which if we do keep change flip, that's 2 pi times 2 over 1, which is 4 pi. So you can see now what happened. In the last example we had 2x and it made it shorter. It squished it down. When we have 1/2, when we have a fraction, it actually stretches it out. So it's like an inverse relationship. If we have a big number, it squeezes the graph down. If we have a fraction, it stretches it out. So let's look at what this would look like on our example. So again, we have our same basic sine curve with the same contact points here. But now, if we start with our basics, 0, pi over 2, pi, 3 pi over 2, and 2 pi. If we're doing transformations, what did I say? The first thing we want to do is divide everything by k. Well, our k is equal to 1/2, so we're going to divide everything by 1/2. Well, what's the same as dividing by 1/2? It's the same as multiplying by 2. So 0 times 2, 0. Pi over 2 times 2 is pi. Pi times 2, 2 pi. 3 pi over 2 times 2 is 3 pi, and 2 pi times 2 is 4 pi. So these values are now 0, pi, 2 pi, 3 pi, and 4 pi, which again, this is where we can check. It's telling me my period should be 4 pi. Well, it is. It took a distance of 4 pi for this sine curve to make one complete cycle. All right, now let's address the third change that we can have to this graph, which is phase shift. So the sine and cosine curves y equals a sine, and now you see we have parentheses here, k in front, so sorry, sine of k, x minus b. Or we could have y is equal to a cosine of k times x minus b. Again, k has to be 0. That's going to be our period number. So these all have amplitude a, or absolute value of a, period of 2 pi over k. So that hasn't changed. Our amplitude is still figured out the same way. Period is still figured out the same way. But it has phase shift of just b. So we have to have this minus sign in here. And whatever it is, x minus this value, well, that's our phase shift. So if I have x plus pi on the inside, I actually have to account for that negative. It has to be of the form x minus b. And whatever that value for b is, that is actually our phase shift. Another thing to point out here is that the value in front of x is equal to 1 on the inside of the parentheses. So if I had a 2x minus pi, I have to have x by itself, so I'd have to factor out a 2 out of everything inside the parentheses to get x by itself, and you will see problems like that. So just remember that if you see a value in front of the x that's not 1, you need to factor that out of both x and b. All right, let's look at an example of this kind of problem. So let's say we have y is equal to sine of x minus pi over 3. So again, let's recall for a minute, if I had something like f of x is equal to x minus 3 squared. So we're going to forget about trig functions for a second. Go back to Math 126 if you came from Math 126 class. When we have a function like this and we have a number inside the parentheses, what does that indicate to us? That's our horizontal shift. What I like to teach my students is the acronym IHOP. Everybody likes pancakes at IHOP. IHOP stands for inside horizontal. So we know it's a horizontal change. And the OP for opposite, because it's the opposite of what we see. So this would be a parabola because of our x squared basic function, but because of the minus 3 on the inside, instead of going to the left 3, it's the opposite. It would be going to the right 3. And it's the same idea here. So we can see amplitude is 1, period is still 2 pi. Nothing changed there because of the 1 in front of the parentheses. We have a 1 in front of the x, so we don't have to factor anything out. So the only thing we have here is a phase shift. And it's a phase shift of whatever is after the minus sign here. So it's a phase shift. I see negative 3, so it's a phase shift of plus pi over 3. So what does that mean in terms of our graph? So because we're going to deal with phase shift now, let me leave the vertical line off at the present moment. So what were our values before? It was 0, pi over 2, pi, 3 pi over 2, and 2 pi. This phase shift of plus pi over 3, so before our graph would have looked like what? Because it's our sine function, it would have been something like that. If it was just sine of x, that would have been our graph. But now, because of the plus pi over 3, it's going to shift all these points to the right because I see negative, which means I have to go the opposite way. I have to go positive pi over 3. So I'm going to go a third of the way this way. I'm going to go a third of the way here, a third of the way here, a third of the way here, a third of the way to the next one. So this one actually then starts here, tops out here, so at all these points, it's still the 5 points, but they've all shifted over a distance of pi over 3. And once we get into some more of the complex problems, I'll show you how you can calculate those exact values. But just the concept of what's going on when we have this x minus pi over 3, it's a phase shift of plus pi over 3. So it takes the entire basic graph and shifts it over. All right, that ends video 2 for section 5.3. Come on back, we're going to work some more complex examples, the ones you're going to see in the homework, and more importantly, on your midterm exams and on your final.